This video will show you how to set up the integral for this homework problem. And this is the first of two videos. In this one, it will be a simpler problem because everything's in one dimension. And this will make the integral easier, so it's a good introductory video. And in the second video, I'll do a more complicated problem where the point is off the bar at some point so that you have two different dimensions to worry about. So in this problem, we have a long, thin bar. We know its total charge Q. It has uniform charge density. We know its length L, and we know how far away point P is. It's a distance A away. And the question is, how strong is the electric field at point P? And this is a positively charged bar. Even before doing any calculations, we know that that electric field has to point right by the linear symmetry of it, and that if we make A bigger and move point P farther away, this electric field will get weaker. If we make the charge bigger on the bar, the electric field will get stronger. So we know all those things. I'm not going to do every part of this problem or even plug in the numbers that are given. I'm only going to do the hardest part, which is to set up the integral for finding the electric field. The general method is the method we use for any of these. And notice you cannot just simply use one of your formulas for outside a ball of charge, for example, or a long cylinder or a flat plate. This is not one of those geometries, and it does not have any kind of Gaussian symmetry. There's no Gaussian surface you can set up around it so that the faces have a nice constant flux and you can simplify it. So it has to be done by summing up a lot of little points. So here's the general method, and I did this in class once. There are some handouts on it in topics. So you've seen this before, but now we're doing it with perhaps the simplest example problem. Here's the bar shown in outline, and the dimensions are given and so forth. And what we're going to do, since we can't use the bar all at once, it's not all the same distance from point P. The charge right here is a distance A, and the charge right here is a distance A plus L, but there's all these charges in between. So what we do is we pick a piece of the bar. You take a piece of the bar as a representative, and you find out what kind of field strength it creates at point P, and you write that as a formula, and then you say, okay, what if I let that piece, pick a piece here, 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 how will that formula change? And I sum up the contributions of all those pieces. I sum up all the little electric fields they make, starting with a piece here makes a little electric field, a piece here makes a weaker electric field, all the way down to the end. And I sum those up, and since I said the word sum, that means we're doing an integral, right? What do we use for the symbol for how much charge this thing has, this little piece? We use dq. That means a small amount of charge, right? And that creates a small field here. And what symbol should we use for the small field? We use dE. That means the small amount of field created by that small amount of charge, okay? And this is our method. We're going to find the total E as the summation of all the little dE's contributed by all the little pieces starting here and ending here. Now, I didn't use any vector symbols because we don't need to keep track of direction. We know the direction is to the right. So we're just summing up strengths. Every little piece from the piece here to the piece at the end creates a small electric field pointing to the right at point P. So I don't have to worry about any trigonometry or any vectors. That's why this is a simpler problem. Okay, we could start thinking about how strong this dE will be. This little electric field would be created by this little charge. And this little charge, even though it doesn't look like a point, it's very, very small, so we consider this to be a point charge. So we use that the little electric field, we're going to use what's called Coulomb's law, or the formula for the field outside a point charge. The Coulomb's law constant, 9 times 10 to the ninth, which is represented by K, times the charge, which in this case is dq, divided by the distance. And now, because I need distance squared, divide by the distance squared from here to here. So now I have to start adding some things to my diagram. That distance is A plus whatever we're going to call this. And notice, if I start with a little dq here, and then here, and then here, and here, and here, all the way to the end, the A is not going to change, but this distance will. So I need a name for this distance that changes as I pick different dq's along this bar. And let me just remember, the bar has a total charge of Q. Okay? So for that purpose, I'm going to create an x-axis through here that points this way. That's the direction of positive x. And, of course, we'll label this as x equals 0. And the end, remember how long this bar is? This is x equals L. And that means wherever I am, I'm going to call this distance x. Okay? So this would normally be over distance squared, d squared or r squared. We'll use r squared because that's what's in your equation sheet. But r equals x plus a. X plus a. X plus a. That's the distance from the little charge to the point. So dE equals k dq over x plus a squared. That's the formula for the little electric field created by any little bit of charge along here, whether I start here with x equals 0 or whether I go to the end where x equals L. Okay? And I could even write this in integral form like that, dq. Okay? All right? Now we have a problem, though. The problem is our integral ends in dq, but we have a variable letter here, x, that starts at 0 and ends at L. So the problem is we have two variables. Two variables, and to do an actual integral, we have to have it in one variable. Which variable do you think we're going to use? Well, dq is a useless variable. We cannot use q as a variable because we don't have a value to start with and a value to end with. That doesn't make sense. And I've made the point a couple of times that your variable of integration will be a spatial one in this chapter. It could be x, it could be theta, it could be r, a spatial variable like that. It could be y, a spatial variable. So we're not going to get rid of the x, we need to get rid of the dq. So how do we do that? We need to replace dq with something. Well, let's look at our original bar. It had a length or a charge of q and a length of L. And we picked a little piece of it, which had a charge of dq, and we need a name for this here. And since our variable is starting at x equals 0 and ending at x equals L, we need a name for that thing. So we're going, what do you call that little width there? We're going to call it dx. So we pick a little piece that has a width of dx and a charge of dq. And we want to replace the dq with something with dx in it. So we do this the way we'll do all of these in this chapter by setting up a proportion. The little charge divided by the little width equals the big charge divided by the big width, or length. You could also set this up as little charge over big charge equals little length over big length. You'll get the same result. So you get dq is that ratio of these two to dx. Now in the solutions, I just call this lambda for linear density. Same thing. It doesn't matter. Since the original problem gives us capital Q and L, I'm leaving it in this form in this video explanation. Okay, so on the previous page, we had this integral. Okay, we'll write that again, k dq over x plus a quantity squared, right? Coulomb's law constant times the little charge divided by the distance squared. But now we're going to replace the dq with this. So we get kq over L. I've put all those together because those are three constants. Then instead of dq, that's the q over L dx, so dx. And on the bottom I have x plus a quantity squared. I'm going to sum this up from the initial x, which remember was 0, starting with x equals 0, and ending at x equals L. And that's where we're going to stop, because this is an integral you can do. It's just calculus AB. You can plug in numbers that are given in the problem. All the rest can be done. The hard part is over, which is setting up the integral. So I'll quickly summarize the steps. There's no formula that can work for the bar. There's no Gaussian symmetry to it. So what we have to do is take a small piece of the bar, all pieces at the same distance from the point. That's how you choose this. And we write an expression for the little electric field created by that piece. And then we're going to start with a piece here and end with a piece there, go all through them. And so for the distance that any one piece is at, we need a variable because this part of the distance is going to change. So the total distance r is x plus a. Put that in, but you have two variables. So you need to replace the dq with something in dx. And to do that, we set up this proportion. Little charge to little length equals big charge to big length. Plug that in, and now you get an integral you can do. Everything's in x. There's x there, and there's dx there. Everything else would be a constant in the problem.